Hey everyone, today I'm going to tell you about an intriguing conjecture that came up while we were thinking about how to make neural networks more robust. This is joint work with my longtime collaborator Yuanju Lee and my intern from last summer, Dheeraj Nagaraj, who is a student at MIT. All right, so let me jump right into it. So this is coming back to my previous video on how to make neural network robust, not robust, sorry, to how to make them compact and memorize. So we're going to be talking about two-layer neural networks. These are functions of the following form. They take an input x in Rd, and they map it to a function of the following form. It's a sum for L equals 1 to k. So we have k neurons. And each neuron, what it computes is first an affine function, wl.x plus bl. wl is a vector, bl is a real. So this is the affine map that the vector computes. Then it applies a nonlinearity psi. Psi is some fixed activation function that goes from the real to the real. So this is the output of the else neuron, and then all these outputs are linearly recombined. So the final output is the sum of AL psi of WL dot x plus BL. ALs are also real number. Let's call f k of psi this set of function. The small reminders that you need from the last video on small compact neural networks to memorize is the following. So here is a reminder. Any data set. So this is a set of pairs input output xi yi. And for normalization purposes, let's say that the xi are in the unit sphere. Okay, so these are d-dimensional vector whose Euclidean norm is equal to 1. And the yi, to simplify, we're just going to be interested in classification, so they are either -1 or +1. So any data set can be memorized, meaning that there exists a function f in my two layers neural network with k hidden neurons. There exists f in fk of psi such that f of xi is equal to yi. So at any input point, it exactly remembers what is the output yi. Provided, so there exists f, provided that k, the number of hidden neurons, so the size of the network, k, is larger than some constant times n over d. And say psi, the nonlinear activation function, is the ReLU. Okay, ReLU of t, which is defined as the maximum between 0 and t. Okay, a very simple nonlinear. All right, so let me just say this again. So any data set can be memorized with a pretty small neural network. How small? Well, you need the number of degrees of freedom, k times d, to be larger than n. Okay, why do I say it's the number of degrees of freedom? Just notice that each neuron is described by d plus 1 real numbers, right? D numbers for the vector WL, 1 for BL, 1 for AL. So k times d is kind of the number of degrees of freedom of my network. And I need this number of degrees of freedom to be larger than the number of equations that I want to satisfy. Okay, I didn't say it, but my data set I, so I is from 1 to n. Okay, I have n data points. So I have n data points in dimension d. All right, so this is what we saw last time. This goes back to 1988, and it's a very simple thing to prove. Now, the question that we ask in this work, question is, what if we also want f to be robust? Okay, what do I mean by that? I mean that it's stable. So if I give it x, it outputs f of x, and I want that if I give it a point which is close to x, then the solution is also going to be close to f of x. Okay, so this is just the definition of Lipschitzness. So what if we also want f to be robust? Say the Lipschitz constant of f is some constant. Of course, this is not possible for every data set. Like some data set, you need to very, very quickly. Maybe, there are two xi's, two input, which are very, very close to each other, but the yi on one is +1, the other one is -1. So then you just cannot be Lipschitz. So just to discard those things, we're going to assume in this entire presentation that the data is random. So precisely, say data is random. Okay, so random means that the xi's are uniformly random on the sphere and the yi are random plus minus 1. Then there exists a function g from Rd to R such that g of xi is equal to yi, and with high probability at least, the Lipschitz constant of g is equal to O of 1. Right? Why is that? It's just because in high dimension on the sphere, most points are going to be far from, all points are going to be far from each other. The distance between any two xi, random xi on the sphere is going to be, larger than 1, basically. So then you can just, this function g can just get the value, let's say +1 at x1, and drop to 0, in distance, let's say 1/2, and then it can go back to +1 at another xi or -1 at some other one, and so on and so forth. And within the distance 1/2, it goes from +1 to 0. So this is very Lipschitz, very smooth. So the question is, there exists such a function g, these bumps. Can you do it with can you be Lipschitz like this with a small neural network? So can you do it? And do it, I mean, get a Lipschitz constant to be of order of a numerical constant with k of order n over d. Can you both be optimal in terms of size and optimal in terms of smoothness? And our conjecture, that we don't know how to prove, says that you cannot do that. It is impossible to be optimal both in respect of size and in respect of smoothness. You have to choose one or the other. Okay, so this is I think somewhat unexpected. Let me just say that in practice, people have known now for quite a few years that making your neural network bigger helps a lot for robustness. So it has been known that overparametrization is helpful to get robustness. What we're saying here is that overparametrization is necessary. You cannot be optimal size and be robust. You have to overparametrize if you want to be robust. Okay, so what is the precise mathematical conjecture? Let me write it. So conjecture. So with high probability, with respect to the jaw of a random data set, any f in fk of psi, so any one hidden layer neural network with k neurons that memorizes the data, so such that f of xi is equal to yi, must satisfy that the Lipschitz constant of f is at least a small constant times square root n over k. Okay, so our conjecture, our main conjecture, states a lower bound. You need to vary at least a certain amount if you have a few number of neurons. You see that this right-hand side, the lower bound on the Lipschitz constant, is increasing when k is decreasing. So when you get a smaller network, you need to have a bigger Lipschitz constant. And moreover, this is achievable, meaning that for most data sets with high probability, there exists, in fact, a neural network with k units that memorizes data and whose Lipschitz constant is square root n over k. Okay, and we don't know how to prove the lower bound, and we don't know how to prove the upper bound. For the upper bound, although we have a lot of hints and we're very close to proving it fully, I will discuss it a little. So let me just spell out really what the conjecture means in two extreme cases. So here is a corollary. Any optimal size network Okay, so remember what is optimal size network? Any optimal size network, meaning K is of order n over d, cannot be robust. Okay, so small neural networks, they just cannot be robust. And what do we mean exactly? Well, the conjecture says that the Lipschitz constant has to be, in that case, at least square root d. Okay, so the Lipschitz constant has to grow with the dimension. On the other hand, any smooth network, meaning that the Lipschitz constant is of order 1, must be very large. And how large exactly? Well, K should be of order n. You see, in the conjecture, if you want the Lipschitz constant to be of order 1, you need K to be of order n. You need basically one neuron per data point. So it's huge overparametrization. Okay. All right, so this is the conjecture. It would be great to prove it. And what I'm going to do next is to tell you a little bit what we know about it, both for the upper bound and for the lower bound. Okay, so let's start gently with the upper bound, which is the easier part. So upper bound. And let's do first the optimal smoothness regime. So optimal smoothness. So in that case, according to the conjecture, we can allow ourselves to have k equal to n. Well, if you have one neuron per data point, your life is very, very easy because one neuron can perfectly correlate with one data point. So let me draw the picture. So we're in high dimension, right? And we have our points here on the sphere. They are all very far from each other. And what does it mean that they are very far from each other? It means that if you draw this cap here of, all the points, so let's say this red region are the points whose correlation with this data point, let's call it xi, the correlation with this data point is, let's say, 0.9. Well, this cap is empty. It does not contain any other point. And more than that, in fact, all those caps are disjoint from each other. Okay. So what you can do is now you can build a very simple neuron like this. You can just do ReLU of xi.x minus 0.9, and let's say 10 times this. So what is this neuron doing? You see, in this green region, which is the region where the inner product is less than 0.9, the ReLU does not activate. Okay, so the neuron does not fire on this green region. So this outputs 0 for any x equals xj, j not equal to I. So for any point in the data set which is not xi, this neuron will give you 0. It will just not activate. And for x equals xi, what happens? You get xi.xi, which is 1, 1 minus 0.9, times 10, 1. So for x equals xi, it returns 1. Okay, so now you can just combine those neurons with the appropriate sign. This will perfectly memorize your data set. And this is very Lipschitz. You see on the red part, this is 10 Lipschitz. Okay, and because this area of activation, the zone of activations are disjoint from each other, the Lipschitz constant is 10 on the entire sphere. Okay, so this is done. All right. So this is one extreme case, the case of optimal smoothness, where you have one neuron per data point. Let us look at the other extreme, which is the optimal size. Optimal size. So the optimal size regime is a little bit harder. And for this part of the talk, I'm just going to assume that optimal size with n of order d. Okay, and I will make some comments about what happens when n is larger. Okay, but let's assume now, for sanity check of our conjecture, let's see what happens if you ask to have an optimal size when n is of order n over d. Then n over d is a constant. It's maybe 1. Let's say n is exactly equal to 1, meaning you have a single neuron, so you're just doing linear regression. Okay, so n is equal to d, you're doing linear regression is the Lipschitz constant going to be square root d? So what you want is you find w such that w dot xi is equal to yi. Okay, the solution to this is just going to be to invert the X matrix and apply this to Y. But the X matrix, because you're in high dimension, the X matrix is close to the identity. It's not quite the identity, but it's close to the identity. So when you invert it, X inverse, it's not exactly that, but let's say X inverse applied to vector Y, this is roughly Y, vector Y. So the norm of this, okay, this is the Lipschitz constant. What is this? This is square root d. Okay, we have endpoint is square root d. Okay, so square root n over k, again in this case, is square root d. So we have checked again the upper bound in this case. We know that you can get an optimal size network whose Lipschitz constant is square root d. And the conjecture says that you cannot do better. Okay, even if you give a constant more number of neurons, you're not going to be able to improve the Lipschitz constant. Again, this is just in the very simple case where n is equal to d. It's the story gets more complicated if you want n larger than d, and I will comment on this at the very end of the video. Okay, so this is it for the upper bound at this point. Now let me move to the real question, which is lower bound. Okay, what we really want to say is that the above construction, which are completely trivial, are also the best thing you can do. Okay, so it's a bold conjecture in some sense. And let me start with a very simple theorem. It's very simple, but it still tells you something. So notice that f of x, my neural network, I can write it as a times psi of wx in matrix notation. Okay, so w is a matrix whose else row is the else neuron, wl, and B is a vector with the biases B in it, and A is a recombination weight vector. Okay, so this is just the sum of AL psi of WL dot X plus BL in matrix notation. So the first comment is that the Lipschitz constant of F, there is a very simple upper bound on it in terms of the spectral norm of W. Namely, it's upper bounded by the norm of A times the Lipschitz constant of psi times the operator norm of W. Okay, so this is trivial. If you want, you can just view it when you take the gradient. You know the gradient, you're going to have A transpose and the gradient of psi evaluated at a bunch of points. You know that the norm of the gradient of psi times the W matrix. So the gradient of psi is a vector whose norm is smaller than the Lipschitz constant of psi. And you do it times W. So how much can you expand this norm? You can only expand it by the norm of W operator. And all of this is recombined by A, so you just get norm of A. Okay, or you can just do f of x minus f of y by Cauchy-Schwarz is smaller than the norm of A times the norm of psi of wx minus psi of wy, let's say. It's upper bounded by Lipschitz constant of psi times Lipschitz constant of w times x minus y, which also gives you the. Okay, so this is trivial. And now let's call this the proxy lip of f. Okay, the proxy for the Lipschitz constant. And the more interesting part of the theorem is that the proxy Lipschitz constant of f is larger than some small constant times square root n over k with high probability, or let's say in this case, I'm just going to prove it with positive probability to simplify, with positive probability with respect to the drawing of the data set with positive probability for any f in fk of psi such that memorizes the data, such that f of xi is equal to y. Okay, so I just need to prove to you the second inequality. Again, the first one is completely trivial. Okay, so let's do this. So the proof. So in our previous work, so this is myself, Ronan Eldan, Intat Lee, and Dan Mikkelinser, we proved that again, with positive probability, what we have is that the Lipschitz constant of psi times the norm of A times the Frobenius norm of W. Okay, so the sum of the square of the entries, the square root of that, this has to be larger than some constant times square root. Okay, so let me explain. I won't reprove this part, but let me explain very simply. The left-hand side, the Lipschitz constant of psi times the sum of the square, basically in the network. This is an upper bound, or this is a bound. This is an upper bound on the Rademacher complexity of this function class. Now you know that the generalization of this function class is going to be governed by the Rademacher complexity divided by square root n. So in particular, on random data, you know that you cannot generalize, okay, because the data is completely random, so you have no idea when you get a new point whether it's going to be +1 or -1. So you cannot generalize, which means the Rademacher complexity has to be larger than square root n. Okay, so that's the proof. It's very, very simple. So now all we need to do, you see this proxy of the Lipschitz constant, it talks about the operator norm instead of the Frobenius norm. And the two are just related by a square root k factor. So let me just show this to you very simply. A Frobenius norm, this is square root of the sum of the singular value squared, which is smaller. Notice that W is of rank k because we have only k neurons. So this is smaller than square root k times lambda max squared. But lambda max, the largest singular value, is the operator norm. So this is square root k times the operator norm of W. Okay, and that's it. That's the end of the proof, right? Because now we know combining those two inequality, the Frobenius norm is smaller than square root k times the operator norm. So if I replace Frobenius norm by operator norm, I just replace the right-hand side by square root n over square root k, okay, which is exactly what we want. So again, this theorem, super simple two-line proof. It tells you that when you care about this proxy upper bound on the Lipschitz constant, it's very easy to prove our conjecture. But of course, this is only a proxy. Okay, it doesn't really capture all the intricate cancellations that you could have in your neural network. So it's very, very far from proving our conjecture. All right, so let's see another result where we really lower bound the true Lipschitz constant. Okay, so here is another theorem, but you will see that when you want to bound the true Lipschitz constant, things get more complicated. So here, while before it was for any activation function psi, this theorem is going to be specifically for the value. So for psi equals value, we have with high probability any f in fk of psi such that, again, it memorizes f of xi is equal to yi. So we have with high probability for any f that memorizes that the Lipschitz constant of f is larger than some small constant times square root d over k. And here we assume, which is the interesting case, that n is larger than d. All right, so this theorem proves a certain lower bound on the Lipschitz constant, which has the correct properties that as k decreases, as you make your network more and more compact, the Lipschitz constant is increasing. In particular, if k is a constant, it tells you that the Lipschitz constant has to be larger than square root d, which is interesting in the region where n is of order d. But it's very, very far from proving the theorem because, if n is much larger than d, let's say d to the 100, this is capped at square root d, whereas you would want a much larger Lipschitz constant lower bound. Maybe to put it differently, this theorem only tells you something non-trivial when the number of neurons is smaller than the dimension. So you can call this the kind of undercomplete regime, where your neurons, they don't span the entire space. Okay, and this will be used very, very heavily in the proof. Oh, and let me say also, so we assume n is larger than d and no bias terms. Okay, this is somehow important in the proof. So here all the BLs are assumed to be 0. So let's see how to prove this. The proof is kind of interesting. I mean, very short also. So notice that the value of t, you can really write it as the indicator that t is non-negative times t. Okay, so there is a linear part and then there is a non-linear part. So f of x, which as we said before can be written as A transpose psi of wx. Again, there is no bias right now. This we can rewrite it as AX transpose wx, where AX is now the activation pattern. So it's the vector AL times the indicator that the else neuron is firing. So WL.x is non-negative. Okay, L is in K. All right, so with this notation, it should be pretty clear that the gradient of f at x, at all points except a measure 0 set, is just, let's say the transpose of that is just AX transpose W. Okay, so in other words, a ReLU network compute grad f of x transpose x. Okay, very good. Now, what do we know about the gradient of f of x? We know two things. So, one, grad f of x, by definition, it's it lives in the row span of the W, is in the row span of W. It's a linear combination of the neurons W1 through WL, which is, so the row span of W, let's call it that V, this vector space, and the dimension of V is K, because we have only K neurons. Again, the whole point of the proof is going to be to exploit that we are in the undercomplete regime, that we don't span the whole space. So the gradient is it lives in this K-dimensional subspace. But we also know that in this K-dimensional subspace, we can correlate with any xi. So for any I in 1 through n, we know that grad f of xi times xi, so the inner product of this thing is 1. Okay, the absolute value of this thing is 1 because it's equal to yi since it memorizes, and the absolute value of yi is 1. For any I, we know that grad f of xi is correlated with xi. But grad f of xi is the norm of grad f of xi. We also know that it's smaller than the Lipschitz constant, by definition, right? So what do we know? We know that there, in other words, there exists V, unit norm. V is in capital V, okay? So there exists a vector in this K-dimensional subspace of unit norm and such that V dot xi is larger than 1 over the Lipschitz constant of f. So this, we're going to be able to use it now to derive a lower bound on the Lipschitz constant of f, okay? Because we will know that you cannot correlate that well with a K-dimensional subspace. So let's think about it. We have all of these random vectors, all of these xi. They span the entire space, and they are roughly uniformly distributed on the sphere. They are uniformly distributed on the sphere. So if there is a K-dimensional subspace, it cannot correlate well with every one of them. Let's take a very simple case. If we take the first k data points, x1 through xk, and we want to perfectly correlate with them, we can have k neurons that perfectly correlate with them. So the subspace V, let's say, is the span of x1 through xk. Okay, so there is no contradiction that V dot xi is larger than 1 for each one of them. That's no problem. But now we get a new vector. The new vector, it's only going to have correlation 1 over square root d with any of the fixed previous one. So the correlation with respect to that subspace can only be square root k over d. So if the correlation with that previous subspace is square root k over d, this means that this Lipschitz constant has to be upper bounded by square root d over k, which is exactly what we want to prove. All right, so let us see how to prove this. It's going to be very, very simple. It's just one line. So maybe in matrix notation, which will be simpler. So this sentence, that there exists a unit vector in my subspace capital V, which correlates at least 1 over Lipschitz constant of f, you can rewrite it as the norm of the projection on that subspace of xi. So when you project on that subspace, you have at least energy 1 over the Lipschitz constant of f. This is the same way of saying those two sentences. So now let me just use this inequality and get to the conclusion. So we're going to sum all of these inequalities. So we have n over the Lipschitz constant of f. This is lower bounded by the sum for I equals 1 to n of the norm of the PVXI. We prefer to have squares in the norm just because then you can expand them and life is easier. So let's Cauchy-Schwarz this. We get square root of n times the sum of the square. Now, the norm square is just the inner product of the vector with itself. So that's xi transpose pv transpose pv xi. So pv transpose pv is just pv. So this is square root of n times the sum I equals 1 to n of xi transpose pv xi, which we can rewrite as an inner product of matrices. So this is square root of the inner product of pv with the sum for I equals 1 to n of xi transpose. And now this is where, you know, this uniform distribution is going to be useful. We know that this sum of xi transpose is going to concentrate around the multiple of the identity. So what do we know exactly? Well, we know that the sum of xi transpose, if you renormalize properly, so if you renormalize such that the covariance is the identity, for this you need the xi to be isotropic, so you need to multiply by a square root d factor. So square root dxi, square root dxi transpose, so that's a d factor. And you take the average, d over n, then you know in high dimension that this is, and in high dimension meaning n is larger than d in this case, this is going to concentrate around the identity. In fact, you know, with high probability, you can very easily say with exponentially large probabilities that this is smaller than, say, twice the identity. So if this is smaller than twice the identity, then the inner product of PV with the identity is just the trace. Okay, so just trace of PV. So you get square root of n times d over n. Sorry, n over d. N over d times d over n. Now you get d over n times the sum, which is PV times the identity, as we say. And you know there's some constant in front. But now PV is a projection on a k-dimensional subspace. Okay, so you exactly know that the trace of PV is k. So this is smaller than constant times square root n times n over d times k. But this concludes the proof because here we had n over the Lipschitz constant of f, and here we have n times n times square root k over d. So we exactly get now Lipschitz constant of f is larger than some small constant times square root k over d. And I made a mistake. Let me just think. Square root d over k. Yeah, which is what we want. Okay, so you see in the under complete regime, this gives you a proof. So this is basically the extent of what we know. Again, this proof, it's impossible that it tells you something about the general regime. When k is larger than the dimension, it's just not going to work. You need something very, very different. So what I will do, I will make another video about this paper, and in this next video, here is what I'm going to explain. So next video. So the first thing is that I will tell you upper bound with square root d Lipschitz and k of order n over d. So above, I told you in this optimal size regime, I only did it when n is of order d. So what I will do is that I will generalize this calculation. So of square root d Lipschitz, so optimal smoothness according to the conjecture for the optimal size, which is n over d, when n is d to the p, and p is an even integer. Okay, so again, this is far from telling you the complete picture, but it broadens the set of cases where we know how to match the upper bound conjecture. And this will be closely related to a certain tensor construction and interesting properties of tensors. So this is what I will explain. And construction, so the construction in this case will be with psi of t, which is simply t to the power p. Okay, so just the power function. And then I will also explain in that video that in this case, this is optimal. So we can prove a matching lower bound for this case. So again, what it means is that for this case, I mean when n is d to the p, k is optimal size, and I will show that you cannot be better than square root d Lipschitz And this will be more general than just psi of t equals t to the p. So matching lower bounds for this case with any polynomial activation function psi of t, which is a sum for q equals 1 to p of, let's say, cq t to the q. Okay, so what's going to be interesting is that this will broaden the set of cases where we have an upper bound and a lower bound matching the conjecture, and also the connections to tensors are interesting. We will discuss the rank of a tensor, the connection between the spectral and nuclear norm of a tensor, as well as some properties of concentration of random tensors. And that's it for today. I really hope one of you viewers can prove this conjecture. I think it's really a fascinating problem. Thank you very much.